So today we are doing lesson 3.5 notes, which is analyzing polynomial function graphs. So this is an extension of lesson 3.4, so make sure you watch that first. So we're adding a list of more characteristics to our list of polynomial characteristics we learned about in 3.4. So we have our relative maximum, points at which the polynomial's function graph changes direction from increase to decrease, known as hills. And then we have our relative minimum, points at which the polynomial's function graph changes direction from decrease to increase, known as valleys. Then we have our absolute max and min, which is the absolute highest and absolute lowest point on the function. Now, there are times when you don't have an absolute max or an absolute min, and sometimes that's going to happen, you're going to have both. And that happens when your function is going down strictly, okay, in one direction. So if it keeps going down forever, for example, we don't have an absolute minimum. We don't have an absolute minimum because it never reaches a minimum because it just keeps going down forever. So in that case, that's when we don't have an absolute minimum. And the same could be said for a maximum as well. Sometimes you'll have neither an absolute max or min. So now we're going to talk about the zeros. So the zeros of a polynomial function are the points where the function intersects the x-axis. Okay, so we know that we have different terminology for x-axis. Crossing the x-axis, we call them x-intercepts, zeros, roots, solutions. Those different terms that we use to describe these things. And a polynomial function of degree n can have at most n real zeros. Okay, so you know how we always find the imaginary zeros by doing the degree minus the number of zeros? So that's at most how many zeros we can have. And if we have all the real zeros, then we have no imaginary zeros. An even degree polynomial has an even number of zeros, and an odd degree polynomial has an odd number of zeros. And that's always the case. So the next thing we'll talk about, which is new to you guys, is multiplicity. So multiplicity describes how many times a zero repeats itself. If the multiplicity is odd, then the graph crosses at the zero. And if the multiplicity is even, then the graph bounces at the zero. So I want to explain what I mean by multiplicity. So I'll just draw, you don't have to draw this, but an example of a polynomial function that's factored. So we have x minus 2, and then we have x plus 3. So see how if we were to set these equal to each other, zero product property, we would get the zeros x equals 2 and x equals 2. So the multiplicity of the 0 x equals 2 is 2. Okay, we have 2 of them. The multiplicity is 2, meaning we have it occurs twice. So what this means is when we have the multiplicity of 2, it actually bounces on the graph. So it appears like a quadratic. So if you see on the graph here, we have a situation where we have a multiplicity of 2, meaning that 0, wherever we hit the x-axis, looks like it's about -3 in this scenario. That 0 occurs twice. Okay? So what that means is instead of the 0, the equation going directly through the 0, see how it bends at that 0 and kind of bends back around like that? It doesn't actually go through the point on the x-axis, it just hits it and curves around. You guys see that? So see how in this little section of the graph, how it kind of has the appearance of a quadratic. If we look at it like zoomed in, it looks like a quadratic equation. So when the multiplicity is 2, obviously 2 is an even number, it bounces on the graph. It doesn't go through it. It doesn't cross the graph, but it bounces on the graph. Okay? So that's what happens when your multiplicity is an even number, when you have a 0 an even number of times. Now the other scenario that can happen, one of the other many scenarios that can happen, is we have the appearance of a linear function over here. So see how we have a multiplicity of 1. That means the 0 just happens once. So you solve, you get x equals 4, and you only have one of those zeros. It only occurs once. See how here the graph goes directly through the 0. It crosses it. It doesn't bounce around or anything like that. It just goes straight through it. Okay? And that's what happens, and it has the appearance of a linear function in this little section here. If you just zoomed in and looked at that section of the graph, it would have the appearance of a linear function. So that's what I'm looking at right here. How is that linear appearance when a multiplicity is 1? And that's obviously odd, so the graph crosses at the 0. And the last one we'll talk about today is the cubic one. So obviously cubic means we have a multiplicity of 3. You guys know cubic is to the 3rd power. So what that means is it crosses the graph at that point, okay? So obviously odd multiplicity means that we cross the graph, but what do you notice is different about a multiplicity of 1, which is also odd, and the multiplicity of 3? What is the difference in appearance to you guys with a multiplicity of 1 and a multiplicity of 3?
One is like linear and the other one.
Good, yeah, one has a linear appearance and one has a cubic appearance. So while they both go through, see how they both go through the point, they do it a little bit differently. The linear one goes straight through, no problems. The cubic kind of like bends around until it goes through. It takes its time going through it. So to keep this in mind, if the multiplicity, as the multiplicity goes up, it takes more time to go through that point. So if the multiplicity is 5, it's going to go through, but it's going to just bend a little bit more and take its time to go through the point instead of just going directly through it. Does that make sense to you guys? Okay. So they have that appearance of whatever graph that they're emulating, basically. So if it's odd, it goes through. If it's even, it bounces. So the next thing we're going to do is actually use look at a picture of a polynomial and identify the characteristics. Some of these are repeats from what we learned about yesterday, but we're adding some more to the list. So let's go ahead and do the ones that we already know first. And I just want to mention that anytime we do increase-decrease intervals, you always use parentheses and never square brackets, okay? And increase-decrease intervals always talk about the x values. We're never looking at the y values for increase-decrease. They're always dependent on the x values. So let's go ahead and get started on what we can figure out about this. So the first thing I see is I'm going to look at how many turning points my graph has. So as you guys can see, my graph has 2 turning points, right? Do you guys have a question?
No.
Oh, okay, sorry, I thought you said something. So this has a two turning points. You guys see that? So number of turning points is 2. So if you think back to yesterday, or actually technically for you guys it would have been the day before yesterday, what do we know about the degree of the polynomial and how it relates to the number of turning points?
You add 1.
You add 1, very good. So the degree of this polynomial is 3. Now we want to determine if it's odd or even. So this is where we look at end behavior. The graph starts down and ends up. So if you guys remember back to your chart on the front of these notes, anybody remember if this is odd or even? When it's odd, good. Odd. Now we're going to look at end behavior. So I'm going to highlight my graph to get you guys to understand the visual of what's happening in this case. So end behavior. So I'm just shading in my graph to look at end behavior. So as I'm looking at my x values on the left, x value is going to negative infinity. What happens to my function in the green? Up or down? Down. The function is going down, so it's going to negative infinity. It's going downward in the green section. Okay. And on the right, as my x values get bigger in the orange section, what happens to my graph? Goes up to positive infinity. Next, we'll look at the number of real zeros, which is how many times we cross the x-axis. And how many times is that? 3. Next, we'll look at the number of imaginary zeros. Anybody remember how to find that? Subtract the degree minus the number of real zeros, which is 0. And domain we've been doing, domain is negative infinity to positive infinity here. And now this is a new one we haven't talked about, which is the range. So if the domain talks about what all the possible x values are, what is the range?
All possible y.
All the possible y values. So we look at our function and predict where it would go up and down. So if this function went on forever in the up and down direction, would it eventually take on every y value in both directions?
Yeah.
Yes, see the arrows are going up and down. So this range happens to be negative infinity to positive infinity because it has arrowheads on both ends that are both going up. So now we're going to get into absolute max and absolute min.
So I have a question about the range.
Sure,
It
sure.
doesn't matter if it crosses it? Like it doesn't need to cross the y-axis?
No, it doesn't actually need to cross it. The range, because technically any point on a graph is going to have a corresponding x and y value. So eventually it's taking on all the possible y values, it just might not hit the y-axis.
Oh, okay.
Yeah. I know it's kind of weird, but yeah, the graphs are only going to cross the y-axis once.
Yeah.
So now we'll talk about the absolute max and the absolute min. So let's think about where this graph is going. What's the highest value for y this graph will ever take on? Do we know? No, because it's just going on forever up. So this time, there is no absolute max, so we say NA, not applicable. There is no absolute maximum because the max, it just goes on forever in that direction. So whenever that happens, it's NA. And what about minimum? Isn't minimum the same way? It goes down forever, so I don't have an absolute minimum either. However, I do have relative max and a relative min, at least one of each. So relative is like, if you zoom into the graph, which one looks like the max, which one looks like the minimum. Basically a turning point, okay, where we change from increase, decrease, decrease, increase. So my relative maximum occurs right here. Everybody see that at my turning point? And to get the relative maximum, we're going to get the ordered pair of that transition point right here. Okay, see that transition point? Relative maximums look like hills, relative minimums look like valleys. So the relative maximum here is -2, 3. You guys see that? How I got that? So I do want to go into a little more depth about what relative maximum is and how to interpret it, because I've seen a lot of math questions where they are asking you this, but in a little bit of a different way. So I want to talk about that. So a question may be phrased like this. It may say, at what value does the relative maximum occur? So when they ask you that, they want to know where it occurs. And that is always the x-coordinate. The x-coordinate tells you where the relative maximum occurs. And the y-coordinate tells you what the relative maximum is. The maximum is y = 3. So the x is the where, the y is the what. Just be aware if they ask you in that format to give it a response in this format. And that's the same thing goes for minimum as well. So let's go ahead and try the minimum. So the minimum looks like a valley, and we find the coordinates of that minimum. What do you guys think?
1, 4.
Good, 1, -4. Everybody see how the relative minimum is 1, -4. And next we'll talk about the y-intercept, which is where our graph intersects the y-axis, which is, what's the coordinate of that?
0, 2.
0, -2. And let's skip down to I real quick. Looking at the end behavior, it goes down then up. Is our leading coefficient negative or positive? Remember from your chart, down then up is positive, yeah. So if you get stuck on that, you just look at the chart. And you will have access to that on your quiz because your quiz is open notes and whatnot. So
Wait, why is it positive?
it's from that chart on the front of your notes from yesterday. The end behavior down then up means positive odd.
Okay, yeah.
You remember?
Yeah.
So now we're going to talk about increase and decrease intervals. So the reason I erased my graph is because I want to highlight all of this. So I'm going to highlight all of my increase intervals in blue. And I'm going to highlight all of my decrease intervals in pink so you guys can follow them. So let's look at where my graph's going up. So think of it as like you're driving on this graph, like it's like a road. And think of like where you're going uphill and where you're going downhill. Definitely not in Florida because we don't have hills like that here, but you know, if there were hills. So as you can see in this blue section here, the graph's going up. And then notice here that the graph switches at the turning point and it starts going down. And the graph starts going down all the way until I get to the next turning point, and see how it switches around and the graph goes back up again. So you see how I found those increase and decrease where it changes. Everybody good with how I highlighted that? Can you follow what happened there? So blue is where it goes up, pink is where it goes down. You guys see that?
So you read it from like left to right?
Yep, you read it from left to right. Yep. Just like think of like how you read English, think that's the same way you read math.
Because it's kind of confusing because you're saying it's going up, but the arrow is like pointing down.
Don't worry about the arrow. Think of like, I always say like, think of like this is like a hill and you're going like on the road. You start on the left and you're going this way. Okay. So I see what you mean because we kind of like look at it from two different ways. It is kind of confusing sometimes. So increase is where your y values are going up, where your y values are increasing. So increase and decrease intervals will always correspond to the x values. You're never going to use y values for increase, decrease intervals. You always look at the x values where this happens. And you only use parentheses. I know we've done this before, but it has been a while, So my graph is increasing from negative infinity, and then it stops increasing at the x value of -2. You guys all see that, how I got that? So that's the first blue section right here, okay? It increases from negative infinity, the x value of negative infinity, and it stops increasing at -2. Now, oftentimes with polynomial functions, you're going to have multiple increase and decrease intervals. So between them, you're going to put a U symbol, which is called the union symbol, which means that you're just saying increases from here and then also increases from somewhere else. So now my next increase interval is over here, which is at 1 to positive infinity. So it increases from x value of 1 all the way to positive infinity. It keeps going up from there forever. So every x value after that is going to be an increase. So everybody see how I got the increase interval? It's always the x corresponds to the x values, never the y. So now we're going to look at our decrease interval. So my graph is decreasing from x value of -2 until we get to 1. So you're going to notice, because polynomial functions are continuous, meaning that they pick up where the other one leaves off, they never have breaks in the graph, you're going to notice that the increase and decrease intervals kind of like they coincide, like one ends here, the other one picks up at the same spot. So see how this one ends at -2, this one picks up where that one left off, and then this one ends at 1, picks up where it left off. So you're going to notice that that happens. So does anyone have any questions about this one before we try another? You guys feel good about this? Feel okay about it? Now, I do highly recommend that you, if you can, shade your increase decrease, because I find that it's hard to do without it sometimes. So if you're struggling, just take the time to shade it. You know, some of the most common mistakes I see with students in math, like I don't mean to be like harsh, but it's just being lazy about it, like trying to rush through it and not like take the time to actually look at everything carefully. So just take the time, you know, don't make a silly mistake. So let's go ahead and try the next one. So the next one, I'm looking at this polynomial here, and I'm going to look at the number of turning points first. So 1, 2, 3. Everybody see how we have 3 turning points on number 2. 3 turning points. Which means that if I have 3 turning points, the degree of my polynomial must be 4. Now we look at the end behavior of my function, which is what happens at both ends, which means here my function is down and down. So this means that my function must be even or odd? Even, and it's actually even negative. So if you want to put those together, you can. The order is kind of weird on this compared to what we learned about before, but it is even negative. Everybody understand why the end behavior tells us it's even negative? Okay. So the next thing we're going to look at is our end behavior in terms of inner arrows with x. So I'm going to shade this region over here. This is where the x is negative, and I'm going to shade this region over here, which is where my x values are going to the positive direction. And we're going to look at what's happening to my function at these points. So as my x values get smaller going to the negative direction, what happens to my function? Yeah, it goes down negative. And as my function goes to the positive x values, my x values get bigger, what happens to my function? Goes down. Very good. So these both go down. Now, number of real zeros is how many times we intersect the x-axis, which is twice. Which means that the number of imaginary zeros is 2. Very good. Now we'll look at domain and range. Domain is typically, and in this case as well, negative infinity to positive infinity. Now range is where it gets a little bit tricky. In the last case, we had our function going up then down, so it eventually took on every range value. But I don't think that's the case here. Because technically, this function will take on every negative y value going downward, right? But is it going to take on every y value going upward? No. What's the highest that my y value ever goes on this function? 4. So my range is from negative infinity to 4. You always go bottom to top, left to right. Now this is actually a square bracket at the end here because 4 is included. So I know it has like a parenthesis, but just make it a square bracket on that. Because 4 is included. Domain and range, if it's included, you use the square bracket. So now we'll talk about absolute max and absolute min. So does this graph have an absolute maximum? A highest point that it will ever go? Good, negative 2, 4. My absolute maximum occurs where x is negative 2 and it is 4. And does this graph have an absolute minimum? No, doesn't have an absolute minimum. But it does have a relative max and min as well. So relative maxes and mins are just wherever your graph changes direction. So we already have our absolute min and our absolute max, my bad. So let's look at the relative max. So let's look at our relative maximum. So our relative maximum is this one right here. You guys see that? Because that's the other change. That is a hill. So what are the coordinates? It's kind of a gross coordinate, but I think it's, let's see, 1, 2, 2.5, comma, 1, 1.5, negative 1.5. That would be our relative maximum. So see how it's kind of like in the middle of the coordinates? That's why.
Wait, I don't get why it wouldn't be negative 2, 4 again.
That would be a relative minimum.
No, negative 2, 4. Okay.
Oh, right here. That's the absolute maximum. The relative max are all like the miniature ones. You see?
Yeah.
So let's look at, now, we don't have an absolute min, but we have a relative min, don't we? This little one right here. So the coordinates for your relative min are positive 1. Positive 1, comma, 1, 2, 3, 4, 5. Negative 5? You guys see how I got that? 1, 5? Negative 5?
So if it doesn't have miniature, like those miniature things that you're talking about,
Yeah,
would negative 2, 4 be?
Sorry, what?
So if it doesn't have like the miniature loop and it's just like up, down, like the last one, then negative 2, 4 would be the relative max?
Yeah, so, alright. So let's talk about our y-intercept. What's our y-intercept here?
Negative 2.
Good, 0, negative 2. Same as the last one, I think. Now we'll do our increase and decrease intervals. So I like to highlight these to get a good picture of what I'm looking at. So I'm going to do the increase in orange, and I'll do the decrease in pink. So my graph is going up until I get right here, and then it starts going down. And it goes down until I get to the next turning point. And then it goes up here, and then it goes down here. So you guys see how that works, where we increase, where we decrease? It's like a roller coaster where you're going uphill and downhill. Alright. So, let's go ahead and identify these with intervals. So my increase interval goes from negative infinity up to negative 2. Union, and then it goes from, good, 1 to 2.5, good. And then my decrease interval goes from, good, negative 2 to 1, union 2.5 to positive infinity. So the reason we don't use brackets for increase and decrease intervals is because brackets indicate that that point is included in that set. So the problem with that is this point right here in the middle is neither increase nor decrease. It's a plateau. So that's where we stop increasing at that point, but we also start decreasing at that point. So since that point isn't set between increase or decrease, we always use a curved bracket to indicate that's where a change occurs. Okay? Any questions on this one? Yes?
What is the two imaginary zeros?
So imaginary zeros come from the degree of the polynomial minus the number of real zeros.
I have a question about the increasing and decreasing, like I'm kind of confused.
Sure.
So why would it be negative infinity? Wouldn't it be negative infinity to 4 or 5?
You always go by the x values for your increase decrease. So from negative infinity on the x coming from this direction, it stops increasing at negative 2 on the x. Yes.
And then you do the u, and then you do 1 to 2.5 because you're looking at the other one.
This one right here, yep.
Oh, okay. And then same. Okay.
Make sense?
Yeah.
Okay, cool. Alright, so we're going to skip to number 5 and come back to the try on your own problems, because I want to try to finish the lesson before lunch, and then we can come back and try on your own and work together and practice them. So number 5 says, what is the relative local max of f on the interval -2 to -1? So I like to highlight because I feel like highlighting really helps me see what's going on. So I look at my graph and it looks like I'm going from -2 on the x up to 1. So I'm looking at this section of the graph right here. You see that pink section? So that's the section of the graph I'm looking at according to the interval they asked me about. So now we're going to look at what is the relative local maximum, okay? So on this interval, what's the highest that this function goes on the y here? Isn't it right here? You guys see how that's the highest that it goes in that interval? So when they ask you for what the max is, you go with the y coordinate, okay? So it looks like it's at 3.7, so the answer here should be A. Everybody see how I got A on that? All right. So now we're going to look at the next one. I'll do this in a different color for clarity purposes. What is the relative local? Like I said, local and relative are same. From -1 to 1. So -1 to 1 is like this section right here. You see that? So now we're looking at our relative minimum, not the maximum. So the lowest it goes here is right here, which looks to be about -1.5, so 1.4 I guess. So it would be this one here, because that's the lowest that the function goes on that interval. And lastly, I'll do the last one in green. What is the relative local max on the interval? So we're looking at the same interval again, but now we're looking at the local max instead of the local min. So the maximum is right here. Okay, that's the local max, which is at positive 1.4. All right, and then the last thing that we do in this unit is actually sketching polynomials. So when I say sketch a polynomial, we're not expecting it to be as crisp and perfect as if you put it in a graphing calculator and you know the equation. We're just getting a general idea of what it looks like. So like a rough sketch, all right? So we use the characteristics to help us do this. So the first thing I usually like to do is I like to graph the zeros. Okay, the zeros are where we hit the x-axis. So I plot points at all the zeros. And we're going to learn about more in-depth ways to do a sketch as well. So I plot all of my zeros. And I look at the characteristics. So this is an odd degree function. And I can look at the end behavior to tell me what the true end behavior is. So it says as my x values are over here, it's going up. So it's up, and then as my x values go positive, it goes down. So it looks like this. This is what my end behavior is going to look like. And I base that on these right here, figuring that out. So I see what my end behavior looks like. So now I can go ahead and graph this to the best of my ability. So it's starting up, and then it ends up down. So that's your rough sketch of your polynomial. So I know for the hills and valleys, you don't know how far to go with it because it's just a sketch. We're not expecting you to like make it perfect. We will learn about more in-depth ways to do a sketch and determine that, but right now we're just doing rough sketches. So the next one is going to be slightly more tricky, but it's not too bad. It says negative leading coefficient. Okay, so if we have a negative leading coefficient, we know that we're determining it's negative, so we have two end behavior possibilities according to our chart. But we also know the degree is 4. So if the degree is 4, the degree is even or odd? Even. So this is negative even. So what's the end behavior look like for a negative even polynomial? Down, down. So we know it's going to be down and down. I can plot my zeros, which they gave me, so I plot those. And I can also plot my y-intercept at 0, 4, which looks like it's right here. And then this is the trickiest part. It says a double root of negative 2. Now you're thinking a root is a 0, right? But we don't have a 0 at negative 2. So it must be a what kind of 0? Good, imaginary. It is an imaginary bounce, exactly. You guys said it right. It's an imaginary bounce. It sounds really weird to say imaginary bounce, but basically it's a 0 that doesn't actually hit the x-axis. So it's a root, imaginary root, but it bends at that point. We know the graph bends at that point. So let's think through it for a second here. So we know that it ends down. Okay, so we're going down, starts downward, and then it goes at negative 2. Okay, so it's going to look something like this, kind of weird. But basically, it's starting down, and then we get here. It's very hard to draw. Hang on, let me get my pen out. What the heck? Why isn't it erasing it? There we go. So it comes down, and then it gets here, and it changes direction and comes back up like that. And you can make that as big and small as you want, but we know that it ends downward like that, okay? So it kind of goes at the 2 and bounces back up. It kind of like makes a little bend, like a fake imaginary 0. Just like we talked about, you see in the other graphs when you have an imaginary 0, it's got that like little wave, but it looks like it's going to be a 0, but it's not. So that's basically what your graph looks like, and you can check this over by saying, oh, I have 3 turning points, 1, 2, 3, which makes sense because I have a 4th degree polynomial. My end behavior is down, my zeros are here. You can check it over, make sure that you did it right. So you could have also made this wave a little bit bigger if you wanted to. I just happen to draw it small. So does anybody have any questions about this lesson? Alright, so I would like you guys to try the 2 try your own questions. So this is the answer to number 3 on the you try. So look it over and check and see if you have all the same answers as I do. Pause the video, check it over. So here's the answer to the you try number 4. I have to go away from the graph for a second to show you all the answers because it's a long list for the decrease. So I just forgot to put the negative sign on these, so just make sure you adjust that.